All right. So it is indeed true. The doctorate comes from a PhD in quantum physics from Germany, but as you can probably tell from the ridiculous accent, I'm originally from Australia. And I have the pleasure for this morning of sharing something. I think it's always great when you come to subject-specific conferences to also map sort of the space or the territory around all of those. And so obviously one of the biggest components for blockchain is also what happens afterwards when we look at the technologies that sit underneath it. What is there that sits in this space around it? So I'm going to give an extremely non-technical explanation, I think, of quantum effects. We'll have a little bit of fun with it, and then what I'd like to do is walk you through where the technology might go in a very, very brief talk. We've got 20 minutes lined up, but I'd like to do it in 10. So everybody, when they think quantum, they always come to this mental picture of a cat in a box. And as the story goes, Erwin Schrödinger, who'll come up in a couple of slides, when he mentioned, when he was actually coming up with the idea of quantum physics and all of these interesting effects, there was the difficulty of trying to explain how these quantum phenomena manifest in a way that we as humans in our macroscopic world can understand. And so the idea here is that you take a cat and you put him in the box. You have a radioactive isotope. It's a typical physicist kind of thing. A radioactive isotope that has a 50% chance of decaying or not. And that would then cause a hammer to strike, which would release a vial, and the cat would either be alive or dead. And the reason for the complication there is to say that we do not intervene in how the cat dies. It happens in as random a way as possible. I would like to rewrite a bit of history for the next 100 years and say, I think there's a much easier way to describe it. So imagine you take a coin and imagine that you toss that coin in the air. Basically what happens is when it lands on the palm of your hand, that superposition of all possible states will mean that it's either a head or a tail. But what's interesting is not when it lands in your hand, when you observe it, but instead as it's flipping through the air. A coin can be both heads and tails and all possible states in between. So I think that's a really simple way of trying to describe it. And of course, when Erwin Schrödinger came up with this idea, he says, I don't like it at all, and went on to say, I'm sorry I had anything to do with it. And Albert Einstein also, when he came up with this, when he read Erwin Schrödinger's work, he said, if this is correct, it signifies the end of science. Well, I don't think we're at the point where science has ended, but instead we've reached, with quantum mechanics, a new beginning. And where it comes down to it, in essence, is that when you look at the digital systems that underpin everything that we have, everything that we see here is running on some sort of a digital system. What you have there is a bit. You have either an on state or an off state. And unlike traditional systems that can exist in only these two states, quantum bits can exist in the 0 state or the 1 state and all possible quantized states in between. And when you look at it from a very simple perspective, a computer is only able to operate between these two steps. But the power of a quantum computer is that it can actually perform very specific types of calculations very, very quickly. So where a normal classical computer would have to go through sequence, we'd call it brute force in cryptography, go through, A, B, etc. A quantum computer is able to test all of those states at exactly the same time. And so what's interesting now is this heralding of a new paradigm with quantum computing, where we say, and this was an article that came out in November 2017, from climate change to world hunger, Microsoft thinks quantum computing can solve all the world's problems. The reality is that there are lots of intractable problems that quantum computing may solve, but I'd like to get specific on what it is that it can solve and what it is that it can't, and perhaps where that shift emerges. So there are 3 paradigms where quantum is going to help us, and I'll just, rather than using visuals, I'll just explain them quickly. Quantum annealing is the types of calculations that we require when we're doing optimization. So let's imagine we have an aeroplane wing. So Boeing, for example, has a quantum computing division. And what it's looking at is calculating the airflow and optimizing the shape of that wing so that it maximizes airflow in a particular way to increase lift. And so if you did that with a traditional classical computer in the way that we do today, you'll have to model all those different atoms of air and how they'd travel along, and you'd have to model all of those different positions. With a quantum computer, it's a little bit different, because you'll actually say, this is the wing, and these are all the possible configurations that can go from here to here to here to here. These are all the possible different directions, and that actually analyzes all of them at once. Now, the point is that we're not at that point yet where we have a computer that's sufficiently capable, but we'll come to that point shortly. The next part is about quantum simulations. So annealing is an optimization problem. We sort of have that done with classical computers, but simulations are a little bit different. If you look inside to the human body, we're created full of these long chain protein structures and all of these sorts of things. And it's actually really interesting for medical research and for innumerable other things, for cancer research and so on, how all of this stuff actually works in reality. And so the challenge is, these protein strands are so long and the combinations and permutations are so large that it's very difficult to simulate all possibilities using classical computers as we have them now. But potentially with quantum computers, the idea here, especially in something called quantum chemistry, is being able to test all of those permutations and combinations of the way that atoms come together, and that'll help us in the medical field to synthesize new drugs, new chemicals, and also to help us with some of the ailments and diseases that we humans suffer the vestige of. And finally, we come to universal quantum computing. So the holy grail really is here, where we take any problem of any size, of any complexity, and that's a telephone call I have to reject, and we actually bring that to a point where we can solve any problem of any kind. So it's not, as it is currently, that it's specifically limited to very particular kinds of problems, and we'll come to talk about cryptography and some of the underlying structures of blockchain, for example. But where quantum will go to eventually is this point about universality of solving any kind of problem of any complexity of any size. And so I wanted to share with you a rule, and this is part of the way that we think as humans. We're very linear thinkers. And so Roy Amara, who's a past president of the Institute of the Future, actually tried to explain how humans think and how we need to overcome a lot of our cognitive biases in order to try and figure out how to think scientifically, how to think appropriately about the impact of the future. So he came up with a rule. He said, we tend to overestimate the effect of a technology in the short run and to underestimate its effect in the long run. So what does that actually look like? So I decided, being a scientist, I thought I'd actually graph this. So what we have is the way that we humans think technology will kind of affect society in the future. Very linear, right? And if you extrapolate from today into the future, you might imagine that's where we are today. And the future is a linear extrapolation of the past and the present. And as we move forward, what actually tends to happen, and I'm going to connect this with quantum computing, is the idea that it actually grows very, very slowly, and we assume that it'll continue to do so, but suddenly we'll see an exponential upshoot in the technology. And we have this from Moore's law in classical computing as well, the idea of processors doubling in quantity every 18 months. Well, actually what we're seeing is that the very same thing is emerging in the quantum realm as well. So if you see here, obviously we overestimate where we should be in the present, and then we totally underestimate in the future. And so if you recall the blue graph as we take it through the middle, this is actually how things have been developing in what is, relatively speaking, a fairly short timescale from 1998, where IBM's Oxford, Berkeley, and Stanford and MIT came together. One of the toughest challenges, and what this qubit is about having this entangled state. You'll notice the picture that I had at the beginning, that very complicated gold structure. That's a dilution refrigerator, and what that does is cools things down to almost the absolute zero of temperature. And the reason for that is that these qubit states, these quantum states, are very, very sensitive to the outside environment. And so, of course, one of the challenges here is how do you maintain these states in a way that they're not perturbed by the outside environment? Because if you recall the analogy that I set up earlier, we only know that the coin is a head or a tail when we see it. It's when it finally is observed by us. And you could say it's almost like the photons that are falling onto the coin and reflecting into our eyes could also have something to play a part. Well, in the macroscopic world in which we live, of course, that coin is not affected. But if it's an electron that sits in a superposition or a quantized state as a qubit, then anything that comes from the outside might serve to change it. And so it's been a real challenge on a technological standpoint, although this stuff is pretty easy in theory, of course. It's been a real challenge technologically to actually build these things, and not only to create one qubit, but to superimpose lots of qubits together, because obviously this problem, as you might imagine, scales in complexity. But we are getting to a point. In 2008, you might recall D-Wave, subsequently acquired by Google, has gotten up to 28 qubits. But you can see now, especially in most recent times, that number's really shooting up. So we got from 50 to 72 to 128. Unlike traditional classical computers, your computational power scales linearly with the number of transistors. In systems like this, the computational power scales exponentially with the number of quantum transistors or qubits. And so I suppose it begs the question as we kind of finalize this quick synopsis of quantum technologies, have we reached what we call the quantum supremacy? So the quantum supremacy is the idea where quantum computers are able to perform calculations faster than their classical counterparts. And we have tremendously powerful computers, mostly locked away in the United States and now increasingly so in China. They're able to perform tremendous numbers of computations. But in October 2019, Google actually came out and claimed that they'd achieved quantum supremacy, and I'll show you where that sits. But of course, IBM disagrees. Interesting statement from IBM there. I think as we round out, it's good to see where the technology is emerging. And you can see for patent filings for quantum computers by country, you can see that the US was leading, at least up until 2018. But there is a tremendous technological arms race that's actually happening with quantum technologies. And so China, at that point in 2018, was there. I actually happened to be in China, and I sat in as a speaker on a really, really big conference on big data and artificial intelligence. And what I noticed there was that if they were behind, I can promise you that they're catching up and certainly overtaking the Western world in terms of their capabilities that they're developing. I was in Guiyang, in the Guizhou province, and at a conference there, I think there were probably 5,000 to 10,000 attendees. And what they've done, which is really interesting in China, is they've set up localities like they did in the past in the industrial age, where this place would be for pottery, and this place would be for sewing, and this place would be for painting. They've done exactly the same thing now. They've actually put together provinces that only exist to serve particular areas of science and technology. And it's tremendous what China's getting up to. So if this was the patent filings for quantum computers, which is a subset of quantum technologies, this is the patent filings for quantum technology by country. So what we can see is that China is far surpassing the US and the rest of the world in looking at all of the other areas where quantum technologies might be useful. And they came out recently with a claim that they've reached quantum supremacy with a satellite test. So what they did here was shot photons, quantum entangled photons, that is photons that are connected in this mysterious way that Einstein called spooky action at a distance. They're connected to each other, and as they're set off in different directions, if you measure one, you're able to also measure the state of the other at faster than the speed of light. And this is something that till now sort of remains unexplained in conventional science. And so they're claiming that they're able to do this with satellites that are 1,200 kilometers from the surface of the Earth. So they're in a sort of an orbit somewhere between the International Space Station and geostationary orbits of GPS satellites. So to get to the meat of it, how does this all relate to quantum? How does this all relate rather to blockchain? So rather than having a quantum physicist come here with no meaning whatsoever, let's relate it back. Where you look at where we are at the moment, so you look at, if you look at where we are at the moment, we're sort of down here at the 50 to 300 state, where we're achieving what we call quantum supremacy. But as we move up towards 300, 500, or 1,000, this is where the quantum advantage actually starts to help us in practical problems or day-to-day problems. And as we move further to machine learning and the impact on artificial intelligence, it's claimed that that's going to happen in about 2028, and it's about when we reach 500 entangled qubits. And then the question really sits, well, where is blockchain going to be affected, or the mechanisms that we have to secure blockchain? When is it finally going to be possible? And so I suppose the answer to that question is we're getting towards it, but we're not there yet. But if you think about the exponential advances as in any other technology with this technology as well, you'll notice that we're actually not that far off, and it could be a matter of years. And so I suppose the question I want to leave you guys with is how far are we from true quantum supremacy, from the idea of quantum technologies being able to, where Bitcoin's algorithm, for example, would be the only one that we block. I think we can safely say that we're nearly there. This was where Google was, so it was able to do what would have taken a classical computer 10,000 years. It's able to do in a matter of minutes. So we might indeed already be there. So I'll leave you guys with that on quantum mechanics.
Thank you very much indeed.